Okay, welcome back everyone. This week's practical we are going to be talking about representing data, and more specifically we're going to talk about databases, data formats, and also vector spaces. Okay, so last week we looked at how we can see certain real-life phenomena as data, how we can convert them into features, and how we might run some naive algorithms to actually work with those features and maybe do some predictions. Now this week we'll get specifically into data, as I said, because the thing that we haven't been talking about yet is really how to represent data in a file format. Now the first important question to ask obviously is, how do we get data in general? Because I can tell you that, okay, we can represent this as so and so, but this sort of obfuscates the actual sources that we use, right? Now I think we can divide it amongst a bunch of different types of data, and it's important that we get through them so you sort of know what we're generally working with. The first category is pre-mades, and these are data sources that have already been compiled by people, and they have like a clear target, they have a clear prediction task, they have certain information available regarding the data sources and all these kind of nice things that are very ideal to work with as a sort of a starting data scientist. Now the most famous example I think is Kaggle. Kaggle is a data challenge website. They set up certain data mining / machine learning challenges where it's basically your goal to get the highest performance on a specific task that they set. So they hide the test data, you only get the training data, and then you have to sort of figure out some classifier or some predictive algorithm that works best on that set. Now other examples are UCI. They have a very big repository of common data sets, and then Stanford, for example, also offers Snap, which has a lot of network data. Now we might also look at common dumps. So these are big batches of raw data that are generally from the sources that I listed here. So IMDb has a very big dump that has all their movies, their ratings, their reviews. Reddit has sort of the same with different subreddits, all the comments, the amount of points that were allocated to each comment, and Movie Lens has exactly the same as IMDb, but they sort of have this rating system going on that you can very much use for a recommender system for movies. Then there's obviously scientific repositories, and I think these kind of differ from pre-mades in the sense that they always are attached to some paper or some research. So the amount of documentation usually varies. Hopefully it's good, but overall scientists don't really prove to be very good at doing very detailed documentations, probably due to lack of time. So you might have to actually figure out from the paper what is actually in the data. And then we also distinguish web APIs, which are a sort of common interface to gather data from several platforms. Twitter and Reddit are examples. And this allows you generally to really tap into their sort of stream data, so you can really hook into the Twitter feeds, just filter by certain keywords. But obviously there's some rate limit, right? These websites don't really want you to pull their whole data set in, so they sort of limit the access that you have to their services. However, a good thing about these APIs is that the data always comes very nicely structured, so in a very good format for you to work with. And that is exactly what is not the case with web scraping. This is where you do it yourself and you really want to get into the HTML structure of a certain website and select the fields that you need. Now, as you can imagine, every site has sort of a different layout, they have a different information structure, so it becomes very messy if you have to do more than one website. Now this is obviously all from the sort of user side where you are looking for data. Generally, however, if you are working at a company, they obviously have their own data, which is what you're going to work with if you're an employee of theirs, and that is generally stored in databases. So before we get into databases and all these kind of data sources, let's first look at the very basic raw level representation of files, which are different file formats. So within these file formats, we can distinguish three main file types. These are most commonly used, they're very widely used standards, and therefore you will come across these a lot. Now, one of the most simple and popular ones is CSV, comma separated values. It's basically a flat data structure, or something that, for example, opening it in Excel, you could see that it's a table format. Now there's columns which are named by some headers, and then there's rows of data. Generally, this file format uses columns as separators, and then quotes to also include these in, for example, text that you might have in this data. Now, what you will see with the CSV is that there's this very clear mapping from where we have this table of data right here, and then there's like column 1 right here, column 2 right here. And what you will see is that this limits you to having the data that you want to represent in a format that only allows you to really have it in sort of a list or an array, or at least on one line. So everything has to be mapped to these different columns. Now let's say that we want to represent movies as data. You will soon see that this can become quite problematic. So movie obviously has actors. And actors can be with many. They can be with maybe 5, maybe 10, maybe 15. Now the question is, how do you want to represent these in different columns where one row is one movie? So this is movie 1. And then all these actors for movie 1, say that we have 10, have to go into this. Now what we don't want is that we have this massive set of columns where most are likely empty, because if a movie has 100 actors, it's probably on a sort of outlier side. Luckily, however, we have more complex formats, of which JSON and XML are excellent examples. Now what we mean with hierarchical here is that data can be nested. So we might have a movie. That movie has a title, but it also has actors, and these actors can be listed. So this is symbol for a list. And we have like actor 1, the name of actor 1, actor 2, name of actor 2, actor 3, etc. So rather than being this sort of flat representation, we have a hierarchical way of representing our data. Now JSON works with key values, so each title will have the actual title here as a value. So this is the key, this is the value. Because JSON is quite lightweight, it is used for many APIs for NoSQL databases that we will get into a bit later, and overall it's quite a popular format, but it's not as widely used as XML. Now XML very much looks like HTML if you've ever seen it. It has these tags where this might be your data. Then there's a movie. It has an ID. And it has a title. And here's the actual title, etc. So notice that this is also hierarchical. It has different tags rather than these key values. And the main advantage of XML is that it's very industry supported. So there's a lot of software to very quickly look things up, evaluate if a certain schema is according to a structure that you've predefined. So it might throw an error if there is no title for a certain movie. And it easily converts to other data standards. I will go into a bit more detail for the next few slides on these formats. Okay, so let me give you a bunch of more examples where you can see how a certain type of information is more suited for any of these file types. First of all, let's consider this house that is for sale. Now, if you looked at the Boston housing data set, you've noticed that there's a lot of factors that are not necessarily related to the house directly, but more related to the neighborhood. So if things relate to a neighborhood, you can only say as much as you want about this neighborhood, and it all directly relates to the neighborhood, right? So the amount of pollution, the amount of teachers per student, these kind of features, they are all basically one flat structure. Which is, as we can see here, this is a raw CSV file, so it looks like this. Generally, these are the headers right here. And then below are all the values, and they range until they you're out of columns, and then the last column here is the last value here. Now, if you were to load it in Excel or any other data sheets or the information, it generally comes up with this this nice table, right? The headers are already placed, and we can see all the values that relate to these features. Now, this is also the type of information that you will probably see if you are going to buy a house. You have these websites that represent information regarding the house. That is also generally in a flat table format. This is because typically you don't really want to say things about the bathroom, right? It's not like, okay, we have 2 bathrooms. Bathroom 1 has a shower and a toilet. Bathroom 2 has this and this. Obviously you can do that, but it's less common to actually specify things nested for houses. Okay, so let's look at an object that I think really lends itself for a JSON type of file format, which is a tweet. Now, a tweet is obviously an object by itself. But we can also think that, okay, this tweet actually has an owner, right? So it has this user that posted the tweet, and the user probably also has a bunch of attributes that we're interested in. So we can say level 1 should be tweet, level 2 should be user. We can also say we have a user, and this user has many tweets. And then first level is user, and second level are the tweets. And already you can probably think of more difficult information that might be within the tweet. So for example, if there's a mention to a specific user, then you would probably want to list the information regarding that user as well. Same holds for the retweets, the likes, all these kind of things. Now, how would all this information look like if it were to be stored in a JSON format? We can see that here we have a lot of nested elements going on, and there's quite complex information that's being captured within this this format. So we have a datetime object here. There's even a boolean in here. We have the hashtags with the name of the hashtag, but also the indices on where it was placed within the tweet. There's abbreviations for the URL, there's expanded URLs. And as we can see here, the tweet is also associated with a user, and it also lists the information regarding the user that posted the actual tweet. Now, if we were to deal with this type of information in code, it would look somewhat like this. So we ask for the keys for this tweet object. And if it's not nested, we can just roll with text, and it will give us the actual text. Now, if we want the screen name of the user, we say user is level 1 and screen name is level 2. We format it like this, and it will give us this. So for the actual text representation of the hashtag, it becomes a bit more complicated, because as you can see, it's not only nested, it's also in a list. This bracket over here indicates that it's a list. So there might be more entries that don't actually have a key that we can use. As such, we need to use the index number. So this is the 0th hashtag, and therefore we just say 0, and then we ask for the text, and it will give us this. Now, if there were an additional hashtag here, we would obviously call it with 1 rather than 0. Indexing usually starts at 0. So I'm not going to go into great detail giving you all the differences between XML and JSON. I think I already touched upon some of those. But here's kind of a visual overview where you can see how they sort of relate and differ in how they use tags versus key values. The fact that XML also allows for some metadata to be placed right here. But also the fact that JSON is quite minimal compared to wordy sort of XML with all the tags right here. Alright, so now that we've gone through several file formats, we can go into storing them a bit more cleverly. And this we do in the form of databases. Now let's first try to answer the question, what are databases and why do they differ from just storing your files locally? So databases are nothing more than just collections of hard disks. They are generally internet connected machines that host a bunch of these magnetic disks that store a lot of information. Now there's several advantages to this, one of which is because they are internet connected, you can access them remotely. So from the comfort of your own home, you can access this wide amount of data that is stored in this database. Typically, you would connect to them via some IP address or some URL. So say HTTPS, my database. And it will ask for obviously a user and a password like anything else. And once we are authenticated to this database, we can actually submit queries to it to get data from here to there so that we can work with it. Now the most important piece to get this going is the database management system, or DBMS, which is a piece of software that acts between your PC and, or at least the sort of authenticated client here, and the database. Now without the database management system, all these disks are basically exactly the same as the thing that you have on your computer. The way it cleverly handles this data is usually through having different collections or tables, or however you want to call them. Let's just give a quick example of a web shop for this example's sake. So what does a web shop have? So we have products usually, right? That's what a web shop does. Products. And each product usually has a name, some price, and maybe also an inventory number. So how many there are in stock. Now there's also shopping baskets where you can put the products. And these products can be in the shopping basket, right? So there's probably a number of products. And also a customer number who owns the shopping basket. And as we can see, therefore, we also have customers. Now the customers also have a name. They might have some address, etc. And then we can also imagine that from this shopping basket, it also generates sales. And sales will probably have products attached to them. They will have a customer number. And this is probably some smoother transition where it doesn't necessarily need to connect to the shopping basket. Now the sales are probably the most interesting part for data mining, because we can actually recommend products to customers if we know that they bought a certain type of product, right? So we probably also have a table that has different categories. And each category has probably assigned some products as well. So we have a category ID and a product ID, etc. Now these can be a bunch of CSV tables. And the trick is that we want to use all these kind of tables to generate one specific result. So give me the customer that bought more than 10 of category something. This will list you a bunch of information. Maybe you also have some demographic information for the customers. So you can, for example, see that teens buy more of some specific category, or some items might be bought together. One of the more popular examples from data mining is that with associative rule mining, they found out that beer and diapers are usually bought together. So this is what databases kind of facilitate in this regard. We can do advanced queries, as we call it. We can ask for information from different linked sources, and then after get one final result. Now databases are generally split into two types of different ways to handle structure information and these queries. We have relational databases, or structured query language databases, abbreviated to SQL. Some of these might be MySQL, PostgreSQL, SQLite, MariaDB, all these kind of different systems. And the main characteristics of these are exactly the same as I drew before. So they have a bunch of predefined tables. Those are structured, they're relational, they relate to each other. And all the fields are basically predefined. So once you create a database entry, you say, for example, this is going to be only letters, characters, texts, these kind of things. It's going to have a maximum size of 50, which makes it generally very robust to change. So it just throws errors if you exceed these kind of rules that were built on top of it. Now the way that you would upgrade your database in this regard is that you just upgrade the database server that you have. So you just stack more disks, get better hardware for this one system that has the database management system installed. Now this is somewhat different from NoSQL, where we have, for example, MongoDB, CouchDB, Cassandra, Redis. These are the type of databases that are generally asked for when doing data science. And the reason for them being so popular is that they're very flexible, they're very development friendly, because they don't have these predefined limitations. You don't need to define if a certain field has to exist in a document. You don't have to define what kind of data you want to throw in that. And this makes it very sort of non-structured. One product might have different fields, which makes it less robust but also more flexible. Now the main advantage of NoSQL is that it scales horizontally, as that is called. You can add different nodes, so different systems that host their own database management system, and you can just plug them into this one server that controls all the independent nodes. There's many systems that are sort of developed to also distribute the data automatically. All these kind of things make it a very, very flexible format. Now there's key value storages that only do key and value and don't do anything nested. There's databases that run in memory, so are way faster than running from disk. There are database types that focus on documents, that focus on a graph representation. All these kind of things are possible because of the fact that it's unstructured. Now for the following bit we will look at a bit of SQL. I'm not going to go very much into detail, but I want to show you sort of how to construct a database, insert data, and select from it in a very, very minimal example, just to give you sort of a comparison between SQL and NoSQL. Okay, so let's first get into creating, which is this bit of code right here. What you can see here is that we name the data table, we name it station, and we specify a bunch of entries that we expect will be in there. Now see that already we're getting types in place for all these values that we want to store in our database. So there's a city, we expect that it will not exceed the character length of 20. There's a state that will only have 2. There are 2 real numbers here, so latitude and longitude. And we also specify the primary key, which is the ID. Now you have to just imagine that in this big disk thing now exists this table called station that has city, state, etc. So there's a table, and the table knows that these are the fields that need to be in there. Now we have to do inserts. So we first specify which table we want to insert into, which is station. So if we have multiple tables, we can actually specify the name where we want to insert certain values, and then here's the list of values that we're inserting. So first is the ID, there's a city name, state, and a latitude and a longitude. So at this point the database sort of looks like this. We have this flat table and there's several entries here. So there's Phoenix, etc. Then we have Denver, etc. So because it's in this database management system, we can now do interesting queries. So we can restrict fields, which is what we're doing here. So we're saying just return city and state from the database here. And then we also add a condition to it. So we say we want the latitude to be greater, that is what this is, than this number right here. And this query will give us the following result right here. So there might actually be many cities in this table here that are definitely not storable on our local machine, but due to this query we can limit it to the extent that we only get this very small query result right here that is actually stored on our machine. Okay, so now for exactly the same code, but then in NoSQL. Now what you can see here is that by inserting we define the database. This doesn't exist at this point. We are just going to insert and it's going to assume a lot of things. So it's going to assume the name. And by inserting ID, city, state, latitude and longitude, it's going to already assume that we want this table right here that has these entries. So at insert time, it's already creating this database for us. We don't need to specify beforehand what is going to be in there. We can just start inserting. Now these queries right here are for MongoDB specifically. They might look different for different NoSQL database management systems. But this is the way that we find these two cities that have a latitude that is greater than 39.7. So we have the key here, which is latitude. We say it's greater than. This is the special operator to say it's greater than. And for limiting the results, we say we only want city, so that's 1, and state is 1, and the rest is automatically set to 0. So hopefully you will see that this is sort of, it's easier, but it also has a lot of assumptions that it does. So you can imagine that companies with a lot of old software where everything needs to be very much in place in a very structured format would prefer SQL over NoSQL. Also because they have the means to upgrade their database servers that can become very expensive very quickly. Now that you know how we store data in a certain format and how we can use database management systems to cleverly retrieve from a very huge collection, we're now ready to talk about how to represent data so that we can work with it with data mining systems or architectures or algorithms. Now, what we've talked about in this specific lecture is 80% of all work if you're doing data science. It's collecting, discovering, cleaning, aggregating data with queries from different databases or different sources. That can be from the internet, from databases that are already around, you have available, but you need creativity to generate insights that were previously unknown to either you or the company that you're working for. Now, most of this you can actually do manually, so you can visualize certain things, you can test for certain hypotheses that you have just using regular old statistics, and only a very small part focuses on prediction. Now, prediction is where you have so much data or so many fields that it's very hard for you to process, and you need these automatic methods from data mining to create insights that are only available when using machines to do this. So typically 80% of the dirty work we're actually not really focusing on in this specific course. There's many other courses that focus on this. We focus on the 20% prediction. So we're already going to assume that most of the data is in place and sort of clean to the extent where we only need to do sanity checks ourselves and then we can do prediction. Okay, so social media is generally a very easy example for a lot of data that has a lot of metadata. So given that we had this tweet example before, I'm just going to stick to tweets for now and say what kind of information could we get from a tweet and what is within the scope of manual analysis that will still generate very interesting insights without doing any type of data mining with predictive algorithms. So within the text, obviously we have the hashtags, we can have certain URLs, there can be user mentions, and we have emojis. So say that we're tapping into the Twitter stream for, say, a day. We're getting all this data right here, and we can do some manual analysis. What we can see is that because we have time, which is a very interesting component, we can, for example, see what the trending hashtags are, right? If you have your time scale and you see that, for example, Trump is on the move today, probably tweeted something, you can see that from here there's a spike, right? I will be interested to see what kind of tweets happen in this window over here and specifically here, because that's probably what caused this increase. Now with the URLs we might go into detail regarding certain news articles that might have happened here, for example, so we can check headlines. We can see which users were very important during this time, so we can see what the most frequent mentions were. And we will probably have a list of usernames and some frequency. Ranked by the most popular. But more importantly, we can see if this hashtag right here has a positive or a negative sentiment. So sentiment is where we would say, well, the words are overly positive or are overly negative. So this would be plus, this would be minus. And we can do this by using emojis as a signal. So a lot of happy emojis are probably positive sentiment, whereas sad emojis or angry emojis are in the negative department. Now the users that we find within this window can also be of interest because we have certain images that we might use images that they post or their own profile pictures. There's names, so we might be able to retrieve gender, for example. With the images, we might be able to retrieve age. Descriptions might say something about their jobs or their occupations or their interests. And same holds for any links, or if there's LinkedIn, or there's maybe a Facebook account. These kind of things we can all use to aggregate more data. And when we use location, we can map from, say, some specific country, which parts people are tweeting a lot. Now, given the fact that we have user mentions, we know who tweets what, who retweets what, we can have this network of people and basically analyze how certain information propagates through a network, see who has the biggest impact on a certain news story. Without having to do any prediction, right? This is all manual analysis. And this is because it's all, or in some sense, all directly in human readable data, right? We know what we can do. We can sort of discover these patterns by visualizing all this information. Now, we've somewhat touched upon this topic before in the previous lecture, but I want to remind you again how human readable data is not necessarily machine readable data. For example, if we have actor names, these kind of strings, we need to encode in a number. Same holds for the labels right here. Because they're ordinal, these are nominal. This is a scale within some restricted range, and then here we have years that, while rating has an absolute 0, year is something we might be somewhat unsure about. So there are different scales. There's data that we need to transform into a number to actually make it representable to machines. Because if we have numbers, then we can do calculations. So if we want to do regression, we have these actors that are converted to numbers now. We still keep the years, and the labels were also converted to numbers. Now we might decide to drop these because the labels probably relate to the thing that we're trying to predict, which is the target scores. And because they probably have somewhat of a one-on-one mapping, it's going to be a it's going to be a feature that doesn't actually allow for prediction, right? It's just going to read off this list right here and then say, okay, if it's a 5, it's probably between an 8 and a 10. And 4 is probably between 7 and 8 or something, which is, this is not what we're interested in, right? We are interested in what actor makes that a certain movie gets a certain rating. Does the year have some effect? We're not interested in this labeling of quality. So in a sort of flat example that you're probably used to, we have certain scales here. So there's our y and one of our x's. Let's say it's only the actor. So x1 or x0, depending on where you start indexing. And we have probably a bunch of entries here. We want to fit a line that predicts y with the least amount of error as possible given x. Now, as you might recall, there's an intercept and there's coefficients per feature. So x1, and we hope that this approximates y to some regard, so the actual scores. Now the fitting of this line is done automatically. I'm not going to go into too much detail on this, but we can do it analytically. which is a closed form solution, which you don't have to know. The only thing you'd get from this is that you can just calculate the required fit. So it's one calculation. But we can also approximate the fit. And this is generally done using gradient descent. Now for data mining, we're not going to go into detail on any of these. This is machine learning. But we can say, I can give you some sort of intuition where we have our data points. So let's redraw this. We have y and x1. And we can say that for some intercept, so beta 0 has some value and beta 1 has some value, we are then left with some error. So we can take root mean squared error between y and our predicted y given the values of this. And we can tweak the values to minimize the error, right? So if we update this to a certain other value, we can see that the root mean square decreases. So when we place it like this, it might have an RMSE of 0.6. When we place it like this, it might go to 0.7. Then place it like this, it's probably 0.8, etc. And this is done automatically via this gradient descent. This is the only thing you really have to know. So it's basically tweaking these parameters to minimize the error. Now we're going into more detail regarding classification in the next lecture, but I want to leave you with some kind of intuition regarding what differs classification from regression. Now we're going back to our nice comfy 2D space, and whereas with regression we wanted to fit a line to explain a target given some features, with classification the target is actually not encoded within the space. The only thing that we know is that these might be some class, so let's make these little x's. So x is class 1. And let's say dot is class 2. These are our dots. And rather than fitting a line to explain, so to get a sort of formula to predict, we want to fit a line to divide our classes. So rather than wanting to fit a line like this, we would want to fit a line like this for separation, so that we can say anything on this side is class 2 and anything on that side is class 1. And this is what we call a decision boundary. And especially for classification, the following you will see is very handy, which is representing vectors within vector spaces. So what is a vector space? If you didn't have linear algebra or anything related to this, the intuition is sort of easy. We have this graph again, but the fact that we now have 3 vectors with 3 features makes this a 3D space. So you have a dimension per attribute or per feature. So we actually need an extra axis. So we have x, y, and z. So how are these vectors represented? Vectors are usually indicated by an arrow, which you will generally not see them in when there is a visualization of a vector space. Usually you only visualize the endpoint, so it's a dot. Now for this one we might say that feature 1, which is the rating, and feature 2, which is the actor, is on Z, This is on X, and Y is then year. Now we can position our vector given the values that we have here, right? This is nothing more than just a coordinate. So rating 6.5 is probably here, actor 1 is here, and 2016, if it ranges until 2016, is here, right? So we can determine the position by just drawing the lines like this. And our vector will be here. So if we want to visualize it as an actual vector from the origin, we have this arrow that points to there. Now it becomes interesting where this is x1, x2 will probably be somewhere in between because the values are sort of the same, but vector 3 is probably visually also within the range of x1 and x2, but it's actually more at the back, right? Because we have 6 here for the actor, which is our z-axis, so it will be further to the back than these. Now this sort of sense of distance within this vector space is something we can very much use when doing classification. And one of the things I can already hint at is that one of the algorithms that actually uses distance to classify is k and n, or k nearest neighbors. Now k is a parameter that ranges from whatever you want. It can be k is 1, it can be k is 5, it can be k is 10, and k determines how many neighbors the algorithm uses to determine a label. So say that we have a bunch of instances here and a bunch of instances here, and we have this point right here. So this is our training data, right? So we trained on this. The algorithm knows that these are what did we call it before? I think this was class 2 and this was class 1. So the algorithm knows from training, so it's memorizing basically. It knows that these are class 2 and then these are class 1. So if we have a piece of test data where we need to determine is this class 1 or is this class 2, we can look at the k neighbors. So the most close to this, let's say for 2, are probably these guys, and therefore the algorithm can say that this is class 2. Now it becomes a bit more tricky when it's way in the middle. It will probably have this one and this one, then we have a tie. There's a bunch of different ways that we can go about classifying this one, but we will get into more detail later. Also regarding how the distances are actually calculated between this vector and this vector. That's all material for practical 3. But hopefully I've given you enough intuition so that you can safely go into the following lecture regarding classification. Now if there's any more questions regarding this, I'm happy to refer you to the forum. Please ask your questions there.